So, good morning, welcome to the 7th lecture of computational complexity. And so, a slightly different setup today. I'm going to keep the presentation within these lines so that it fits on the video. I realised that the way things were working, I was trying to do things previous weeks wasn't really working. Hopefully this will be better. So let me remind you where we are on the course. We've got our hierarchy of complexity classes. We've been looking at, spell hierarchy correctly. Hierarchy of complexity classes. We started with polynomial time, kind of the idealization of efficient computation, but non-deterministic polynomial time. And we went to space complexity. Deterministic and polynomial space. And when you use polynomial space, even if you're being non-deterministic about it, you stay within exponential time. Exponential time is pretty bad because you would have to wait a long time for large inputs, but still, at least you've got some bound there. And then below polynomial time, we had non-deterministic logarithmic space and logarithmic space. And last week, we looked in detail at polynomial space, and we almost proved, but we didn't quite finish the proof, we almost proved the unexpected equality of polynomial space is equal to non-deterministic polynomial space. At the end of the presentation part, at the end of the lecture part today, I shall return to last week's proof and finish that, but actually we can naturally lead back into it by doing the main topic that we're going to cover today. The main topic we're going to cover is to look at the bottom end of this hierarchy. So where things are better than efficient, here we've got time efficiency. In a mathematical idealization of that, we take a polynomial amount of time. But if we polynomial amount of time, we'll use at most a polynomial amount of space. But sometimes we can constrain the space to much more than that. And so there are these two classes of computations that use only space that's logarithmic in the size of the input. It can be deterministic computation that uses space logarithmic in the size of the input, or more generally, non-deterministic computation that uses space in space that's logarithmic in the size of the input. So today's title is logarithmic space. And how we're going to address this is what I'm going to do today. I'm going to remind you, so I'm going to recap, short for recapitulate. Just tell you again, go over once again, recap the definitions, just write defs of logarithmic space and non-deterministic logarithmic space. Then we'll see some examples of problems in logarithmic space, but more interestingly, we'll see a very natural example of a problem in non-deterministic logarithmic space. This is called the path problem. main result today is going to be that path is NL complete. So again, it's a complete problem. It's as hard as any problem for non-deterministic logarithmic space. As a result, I would have liked to include, but we don't really have time for, and also the proof is very technical. I mean, it's not very long, but it's quite technical. It's a beautiful proof. So for anyone that's interested in it, I think it would be a nice thing for you. I recommend having a look in the textbook to see the proof of this. So an important result we will not cover but this is an important result, is that non-deterministic logarithmic space is the same as co-non-deterministic logarithmic space. So if you've got a problem in non-deterministic logarithmic space, the complement problem is also in non-deterministic logarithmic space. So that's again a surprising result, because with NP we certainly don't know that, and we believe that it's not true. We don't believe that NP is equal to co-NP. With P space we have the surprising result that NP equals P space, and because P space is closed under complement, it's certainly then equal to co-NP space as well. So we get an analogous result for P space, for polynomial space. For logarithmic space, amazingly, non-deterministic logarithmic space is equal to the the complement of any non-deterministic logarithmic space problem is again a non-deterministic logarithmic space, but it is widely believed that nonetheless non-deterministic logarithmic space is a strictly larger class than deterministic logarithmic space. So people believe this inclusion is strict. So anyway, so every particular category of things, here it's logarithmic space, here polynomial time, here polynomial space. In each case, there's some sort of different relationship between the main classes covered out. Right, so let's go to the definition of logarithmic space and non-deterministic logarithmic space. We did this 2 lectures ago, so I'll just remind you quickly so we recall, as we remember that logarithmic space is simply defined to be a set of those languages. So a language is in logarithmic space if it's computable in deterministic time of sorry, I need to put the big O because that's in the deterministic time of log n. And it doesn't matter what base we choose for the logarithm, because the class of deterministic time languages for a given function is defined using big O. Big O, there needs to be a Turing machine that runs in time big O of this, then whatever base you use, you get the same class. And non-deterministic logarithmic spaces, of course, just, sorry, this shouldn't be time, this should be space, it's logarithmic space. Those languages that we can decide in using a non-deterministic Turing machine in space, big O and log n. So I'm going to spend most of the lecture on non-deterministic logarithmic space because it's more interesting. But let me give you a couple of examples of languages that are in logarithmic space. first one I'm going to call div3, divisible by 3. And this is defined to be the set of, so it's a language, so it's a set of strings over the binary alphabet, so over zeros and ones, of all those binary encodings of numbers, such that so n is a natural number and n is divisible by 3. Three is not important here. We could replace it with any other number, and we would still get a language in non-deterministic space. Sorry, in logarithmic space, not non-deterministic logarithmic space. So this is the binary encoding. The more interesting language, called mult, the language of triples. There's tuples with 3 things in it. So you can code this as you might use an extra symbol like a comma or a hash to separate your encodings of numbers. That's an L. So it's triples. By some encoding the triples that use over the alphabet, where the 3 components of the triple are encodings of numbers, and they're encodings of numbers such that L is an encoding of n times n. So we're deciding if one number represents the product of the 2 other numbers. So here we've got n and L are numbers, and L equals n times n. Right, I'm going to show you that div3 is in logarithmic space. It's very easy, and I think you might have done something similar in an early exercise class. I'm going to leave it as an exercise to show that multiplication is in log space. It's a little bit interesting because you use the usual algorithm for multiplication that you know at school. That's fine to use that. But you don't have enough space to, if you were writing it all down on a sheet of paper, you don't actually have enough space to do it. So you have to be a bit careful about how you use the space. Clear the board. Doesn't look like physics.
I think it's very odd.
It could well be, yes. What was this? Crosstalk. Oh, yeah. It looked like photon. Right, so we're going to see that division by 3 is an L, but this is really simple, so let me not take very long on it. So just carry these down. I'm going to show so we're going to have an input word, which is going to be a binary string, and we want to see if it represents a number that is divisible by 3. How much space do we need for that? Does anybody know how much space we need? So how much space are we going to need on a working tape? We're going to have our input tape that has a read-only head. We've then got some working tapes, potentially, that have read-write heads. How much space are we going to need to use up on the working tape? Does anyone have a guess? So that's we're given an input word W. So actually, we don't need any space at all. We don't even need a working tape. So it's very much in logarithmic space. It was even in constant space, if one could define constant space. So we simply scan the word from left to right. And all we, instead of space, I mean, constant space is much the same, but a fixed amount of space is much the same as using the states on the junction. So we have a fixed number of states, and we're going to use 3 particular states, and they do the obvious thing. So we'll switch between 3 states. And these states, I'll call them 0, 1, and 2. And 0, basically they're simply recording the word you've read so far. It represents a number because it's a word of 0s and 1s. You just record what that number, the remainder when you divide that number by 3. So in other words, the word read so far is equivalent to, in this case, 0 modulo 3. In this case, it's equivalent to 1 modulo 3. In this case, it's equivalent to 2 modulo 3. And you can simply define the algorithm that does this by a little graph that tells you how you change state when you read an input symbol. So we're going to start in the state 0, because at the time we read no input symbols, that's essentially got nothing accumulating to our number, nothing contributing to our number, so we're 0 modulo 3. So we start with the state 0. But if we've read a word, so far, if we read some part of the word, let's call it key for a prefix of the word, and this is equivalent to 0 modulo 3, then when we read a 0 after this, well, this number is going to represent 2 times the number represented by p. So if this one was divisible by 3, then 2 times it is also divisible by 3. So if we read a 0, we stay in state 0. If we read a 1, well, then it's 2 times the number represented by p plus 1. So that's 1 modulo 3. If we read a 1, we go to the state 1. If we're in the state 1, well, if we read, so if p is equivalent to 1 modulo 3, and p followed by 0, well, that's 2 times p plus 0. So this is equivalent to 1 modulo 3, so that's equivalent to 2 modulo 3. If we read a 0, hang on, 2 times, that seems right. Read 0, we get 2. If we read a 1, well, then we have 2 times p, this which is equivalent to 1 modulo 3 plus 1. So that is then becomes divisible by 3. So if we read a 1 from here, we go back to 0. And from 2, so p is equivalent to 2 modulo 3. Well, you can work out that if it's a 0, then 2 times something that's equivalent to 2 modulo 3, that's equivalent to 1 modulo 3. So the 0 goes back here, and the 1 will keep us there. So this is how we change the state. We start off in 0, so one often puts an arrow in to say we're starting. And when we finished reading the word, well, we want the word to be divisible by 3, so we accept when we finish reading the word, and one often denotes this by putting an extra circle around here. And such things are called finite automata, but they're descriptions of constant space algorithms. Algorithms that take constant space or even zero space, because you can simply put all the information that you're working with into the states of the Turing machine. You have a fixed number of states of the Turing machine. In this case, we have 3 states, plus we have a special start state that the Turing machine starts in. The start state will immediately go to the 0 state, and then we have the accept state, which is a halting state. And when we've finished reading the word, when we get to a blank at the end of the word, then if we're in 0, we go to accept, otherwise we go to reject. So is there anything else to say? I think that's enough. I've said it. I don't need to write. Well, let me just start in 0 state. If in 0 state at end of input, and we accept. If not in 0 state at end of input, then reject. Okay, so anyway, that's very simple, but at least it's something in deterministic logarithmic space. But now we're going to look at a problem in non-deterministic logarithmic space, and this is more interesting. So we're going to look at what's called the path problem. So I think I can. So this line here is where the end of the video is. The board on the video. Maybe I can rub this off and then we'll give a little bit more. Can I take this off? Yeah. So actually, I'm just wondering, it might be useful to be able to see the path problem. So I'm going to bring the board down again from the top, and we can prove it's an NL on the bottom board. That's the whole thing. Path problem, we're going to show this is a problem that is not known to be in deterministic logarithmic space, but we're going to show that we can solve it with a logarithmically space-bounded non-deterministic Turing machine. So it's in the class NL. The path problem is a very natural problem about directed graphs. So as with these decision problems, the most friendly way of presenting them is to say what the input is, and then what question the decision problem is trying to answer, like some yes/no question. So the input in this case is a triple. So again, a triple is represented just by 3 strings juxtaposed with some nice separating symbol between them. Hash or a comma or something. So we have a triple GST, where G is a directed graph. So that's simply a set with a binary relation on it. But you can think of it as a set of vertices. I mean, we've met the concept before. set of vertices with arrows between them. And now you can come back to the same place. For example, and S and T are two vertices in the graph. The problem is simply, is there a directed path in the graph from vertex S to vertex T? So, a directed path is a path that links the two vertices along the edges, where the directed means it follows the direction of the arrows. Sorry, this is supposed to be the question that we're answering. Is where a directed path from S to T in G. Or we can think of it as a language. So in that case, path is the set of strings. Where the string simply represents a triple G S T, set of strings of the form G S T, so encodings of triples where so G is a directed graph. And there is a path, so with a path from S to T. Where S and T are two vertices, I think that's implicit. So what I want to do is show you that we have an algorithm for deciding this question that uses a non-deterministic Turing machine and works in polynomial space. Sorry, not polynomial space, logarithmic space in the size of the input. So in order to think about how much space one needs in the size of the input, let's think about how long, by the size of the input, I mean the length of the input string, so how long an input representing GST needs to be if we've got a graph of a particular size with a particular number of vertices. So how much length of a string do we need to represent the input to this algorithm? So if G is a graph, a directed graph, with vertices B and edges E. So we can think of each edge. So the edges are simply given by a set of pairs, namely the first one's the start vertex of the edge, and the second one's the end vertex of the edge, where it goes from and to. Then again, we did this before with graphs, we can represent G as an adjacency matrix by an adjacency matrix. which simply, as I described before, you have one row for every vertex and one column for every vertex. And whenever you have a vertex U, a row corresponding to a vertex U, and another the column corresponding to a vertex or V, then we put a 1 in here. 1 if there is a directed edge from U to V. So I mentioned adjacency matrices before for undirected graphs. If you've got an undirected graph, well, undirected graphs, as we were defining them, so an undirected graph, if you have an edge from U to V, it's the same as having an edge from V to U, we don't distinguish. An undirected graphs is normally defined, aren't supposed to have self-loops. So you don't have edges from vertices to itself. So for an undirected graph, you also have such an adjacency matrix representation, and it has a special property that it's a symmetric matrix for an undirected graph, and the diagonal entries are all 0 for an undirected graph. For a directed graph of the kind we're considering now, there's no symmetry in general, and also the diagonal entries could be 0 or 1, depending on, we're looking at a vertex that has an edge to itself. Okay. But anyway, we have an adjacency matrix, I should say, not matrix. And clearly the size of that is big O of the squared, of the number of vertices squared. I mean, you could say the size is exactly B squared bits, but it depends how you represent it, because it might be convenient to have markers at the end of the rows, or it might be convenient to put a bit of information to tell you how many columns or how many rows you have beforehand, which would be a little bit of extra space, but you can certainly, whatever you do, you can certainly represent it in the size of B squared. And now the source and the target, well, these are vertices picked from a set with V elements. So we need enough information to be able to tell us to index an element out of a set of V elements. So we could simply call these elements 0 up to V minus 1 to the size of V minus 1. And then if we were representing them in binary bits, we would need logarithm log to the base 2 of the size of the plus 1 bits in order to represent the index or something like that. So basically, we can represent the vertex S and T using a binary string that represents the position of the vertex in our matrix is written in a certain order, and the position in that order. And the size of that is big O of log of V. So we can represent vertices UV by a 0,1 string of size big O of log of number of vertices. So the relevant thing here, actually all we really need is that the representation of the graph is polynomial in size. So the length of the representation of the graph is polynomial in size in the size of the graph. The representation of the whole GST is polynomial. Size of the set of vertices. So as I think we've already discussed once, there are various well-known algorithms for searching graphs. So we've got a graph and we want to see, is there a path from vertex S to vertex T? Two standard algorithms are breadth first search and depth first search, where, say, breadth first search, we start from the vertex S, we explore the neighbours of the vertex S and see if any of them's T, then we explore the neighbours of the vertex S, and then the neighbours of the neighbours of the neighbours of the vertex S, and all the time we maintain a list, if you like, of the vertices we've seen but have not yet explored the neighbours of, potentially, and we also maintain a record of the vertices that we've already visited, so when we go to visit a vertex for the second time, we know that we visited it before and we don't need to keep on exploring from that. So that's like how breadth first search and depth first search both work, just the difference is the order you do things. That's a deterministic algorithm, but it's not going to help us with a non-deterministic. It's not going to help us it's not going to give us a logarithmic space algorithm, because for both breadth first and depth first search, you need to keep a list around of the vertices that are still in consideration, so that the neighbours of your current vertex, and then they go into a list as a list of vertices to explore, and you also need to keep a record of the vertices you visited. Because the graph is of size V, that's going to take at least V space, at least big O of V space in general. A big O of V, well, the graph of the size of the input is polynomial in V. So big O is actually quadratic in V. So big O of V is not logarithmic in V squared. So that's not good enough. So we need to do something different. Instead, non-determinism is going to help here. So so can anyone see how this works? Just while any ideas? I mean, if it were 5 minutes later, I would give you 5 minutes to think about it during the break, but it's not 5 minutes later. And in any case, I'd quite like to do this and then get to the break. Anyway, think about it for yourselves. But now I'm going to tell you. So the crucial thing is that if there's an obvious fact, if there is a path from S to T in the graph, then there's a path of a length at most V, where V is the number of vertices. So we use the fact exists a path from S to T if and only if there exists a path of length less than equal to the number of vertices in the graph from S to T. And the reason that the left to right direction holds, which is the interesting direction, is that if there's a path from S to T, then if it visits any vertex more than once, well, then it does a loop to that vertex. So you can remove the loop, and you get, in the end, you get a path in which every vertex appears at most once. So there has to be a path of length less than equal to V. So now we can use non-determinism to help, because what information do we need to record? Well, our input to the graph is this G, S, and T. Essentially, what we're going to do is we're going to record two pieces of information. We're going to non-deterministically explore the graph. So each time you're at a vertex, we make essentially a random choice. We just a non-deterministic choice of which vertex to go to. And we simply, all we need to record is the current vertex and the length of the path so far. And if we ever get to the vertex V, we're done. If the length of the path gets to size of V plus 1, and we still haven't, sorry, when I said the vertex V, I meant T. If we ever get to the vertex T, we're done. If the length of the path becomes the size, the number of vertices plus 1, and we haven't yet found T, then this non-deterministic path didn't work. But for a non-deterministic algorithm, we only need one non-deterministic path to work. And if there is a path, then there will be one of appropriate length path, and it will be found by one non-deterministic exploration. So all we need to do, so algorithm at the start, so we can have two working tapes if we want to, then we could obviously put it on one working tape. At the start, we record the vertex S. So let's say the current vertex equals S and length equals 1 on two working tapes. And then at each step of the algorithm, we check to see if our current vertex is T, in which case we're done. Otherwise, we non-deterministically choose another vertex and increase the length. So each step of the algorithm so if vertex equals G equals T, then accept. And we also, before exploring further, we check to see if the length is greater than the size of the graph, in which case we reject, because we failed to find a path of length less than or equal to V. So if length of the path is greater than V, then reject. Otherwise, we non-deterministically choose a vertex T prime with T prime, with such that there's an edge from T to T prime in the graph. And if no such vertex exists, then we reject. If no such T prime exists, we reject. And we increase the increment the so we set vertex. Let's use the old-fashioned computer science assigning a value to the vertex with the current vertex. So the new vertex becomes equal to T prime. Hang on, sorry, I'm using. So this T, I'm being a bit confused here. I mean, it's very easy. So if the vertex equals T, so this should be T prime with that. So we can move to from the previous vertex that we had. And now we reassign the vertex, the current vertex we're at in our exploration to T prime to the new vertex, and we increment the length. So let me just write length plus. Anyway, this means length becomes equal to length plus 1, and that's the algorithm. And we're done. Okay. Good. So 3 minutes past. So I will give you your 5 minutes break. So we'll have a break until 8 minutes past 9. Let me pause the video. Right, okay, so we've seen then that the path language is, I made a mistake here. This is a non-deterministic algorithm, so this should have been a non-deterministic logarithmic space rather than L. And the other thing I didn't emphasize, which I should have done, is how much space it's taking up. Well, the space it's taking up is we're recording, we're using two tapes. I mean, we don't need two tapes, but we can use two tapes if we want. One is recording the current vertex we're at, and the other is recording the length. The length can go up to the number of vertices. The vertex we're at is also a number between 1 and the number of vertices. So let me just add at the bottom. Well, we're at the side here. So both length and vertex take O log the number of vertices space. And the input size, remember, is O of square, the number of vertices. So indeed, one can see that this is logarithmic in this, in that here we've got some constant times b squared, so that's v to the power of c times c times 2, some constant c, take the so anyway, take the logarithm of that, then it's going to be 2 times c times logarithm of b. So indeed, they go log n is the input size. So n is the input size. This is always is. Okay, so that shows that path is indeed in non-deterministic logarithmic space. A very simple idea, quite a simple little algorithm to realize nicely. So the remaining thing I want to do is the main thing is to show that path is NL complete. This complete problem for non-deterministic logarithmic space. There was a good question in the break, which was, why is it important to consider directed graphs here? I spent a bit of time saying I was looking at directed graphs. So actually, if you have an undirected graph, the same algorithm will work to show that an undirected path, the problem of does there exist an undirected path in an undirected graph is also in non-deterministic logarithmic space. The same algorithm works there. But actually, it's very surprising, and this was a big result. For undirected graphs, there's a deterministic logarithmic space algorithm that finds whether or not there's a path between two vertices. So that problem is not known to be NL complete and is thought not to be, because it's thought that deterministic logarithmic space is different from non-deterministic logarithmic space. This problem, however, for directed graphs is known to be complete for non-deterministic logarithmic space, and that's what I wanted to show. It's rather surprising that the problem for directed graphs is apparently harder than the problem for undirected graphs. I'm actually going to rub this part out so that we keep the path problem up there. So let me define what it means to be NL complete. By this stage, there aren't going to be too many surprises in this, but one has to be a little bit careful about one thing, or even two things. So let me remind you, the language L is NP-hard. So I'm just reminding you for NP, if for every NP language, let's take the floor off. So if every NP language sufficiently polynomial time reducible to L, and the language L, if an L is NP complete, if it is both NP-hard and belongs to NP itself. So basic definitions from like the third lecture that underpin the whole course. So if it is NP complete and hard, and if L belongs to NP. Okay. So what does NL-hard mean? So we want to do the same thing. We want to say what it means for a problem to be as hard as any non-deterministic log space algorithm. I'm just going to make the definition, the changes here. So we want to, this is going to, so NP is going to become NL. The NL-hard, that's what I want to define. And now, well, it's going to be hard for non-deterministic logarithmic space languages if every non-deterministic log space language is reducible to it. We change this to NL. We want to say it's as hard as any NL language. But we have to change one other thing. It's not going to be any good to use p-time here, because we certainly want our reduction to be efficient, but the whole idea here is we want to use logarithmic space, and the p-time reduction might go outside logarithmic space. So we want our reduction itself to respect the sort of resource constraints that we're interested in. There's also a mathematical reason that you can't put p-time here, and that I think is going to be considered in the exercise class this week. So it doesn't work mathematically to consider to put p-time here, but conceptually, anyway, it makes sense. We want our reduction to be somehow simpler than the kind of language we're showing is hard. So what we ask for here is for it to be deterministically log space reducible. So I'll just write log space reducible. So this is just the sense of deterministic. And we do the same thing here. So NL complete just means that it's NL hard. It's hard for non-deterministic log space, but the language is itself a non-deterministic log space language. NL hard and NL hard. The other subtle point is to remind you how this deterministic log space reduction works. So here we want a a logarithmic space computation, but it's not a logarithmic space computation that's just producing a yes and accept reject answer. It's one that's producing an output string, because we're transforming some NL language L prime, say we're transforming strings from the alphabet of that language to whatever alphabet L is over. And we want to transform strings from that alphabet to appropriate strings that are going to, that we can look at to see whether they belong to L. So the reduction is necessarily a Turing machine that's producing an output. So we need to remember what it means to be a deterministic, logarithmic space computation that produces an output. There's a little subtlety here that I'll remind you of. So let's see. So remember, log space reductions are affected with an E. That means carried out by, so affected with an A would be influenced by, so that's sort of affected, but the other verb affected in English, so are carried out by, remember log space reductions are affected by deterministic TMs that have, importantly, a read-only input tape and a write-only output tape. And of course, read-write working space tape and read-write working tapes using logarithmically bounded space. So that's the logarithmically bounded space is just for the working tapes. So importantly, neither the input tape nor the output tape, neither of them have logarithmically bounded space requirements. The input tape can't have, because the logarithm is in the length of the input tape. One could ask for the output tape to be logarithmically space bounded, but we don't. So, I mean, computation can take polynomial time. It can be writing on the output tape. It just needs to use only a logarithmic amount of working space. So here on input and output tape, there is no logarithmic space bound. So that's the slight subtlety. Now, our main theorem the path is hard for non-deterministic log space languages. There is NL-hard. And since we've already proved that path is in NL, we've given it a non-deterministic logarithmic space algorithm. So this one that was non-deterministically searching the graph and remembering the length of the path in the current node. That means, so therefore, path is NL complete. Okay, so let's get going on our main proof today. I haven't quite learned how to juggle these two boards yet, so I realise I would have, I would really like to push this board up in a few minutes and before bringing this board down. It just doesn't work in this room. So maybe I shall just do this whole thing on the other board instead. I want to lose the start of the proof. So should have written this at the bottom so you can see it for as long as possible. But path is NL hard, therefore path is NL complete. Remember what path is now. Well, we've lost the definition of NL completeness, but we're going to prove that NL hard. Actually, we just need to show the hardness. So we want to show that any non-deterministic log space language is deterministically log space reducible to path. So suppose L is any NL language. We share L is reducible to path. And this is going to be very similar to our reductions that it's going to use the same idea, the reduction of the Cook-Yevin theorem that SAT is NP hard, and also the theorem that I didn't quite finish from last week, that P space that, QBF, quantified Boolean truth, TQBF, truth of quantified Boolean formulas, is N is non-deterministic P space hard. So that idea is to consider a Turing machine, a non-deterministic Turing machine that's logarithmically space-bounded in this case, that decides L, and to use that Turing machine, to use the details of that Turing machine to get a reduction to path, to build a suitable graph and translate the problem to the path problem. Essentially, we kind of did the idea last week. So we're just going to remind you of it, and then this is also going to lead us naturally into completing last week's proof. So there are obviously just different details to check today than there were last week. So let M be a log space bounded non-deterministic Turing machine NDTM that decides L. And let's actually give ourselves a space bound for it. So let's assume the space is bounded by, there's got to be big O of log of n, where n is the input size. So that means it can be bounded by some constant times log of n. So we're going to have it bounded by c times log of n. And as before, I'm going to assume I'm going to assume two things: that the Turing machine wipes its working tapes before it accepts or rejects. Well, it's only important about accepting. As before, we assume that N wipes, that means cleans or erases, let's say erases, more precise, erases its working tapes before accepting. And also when it goes to the accept state, that it idles on the accept state. Actually, I don't think we need that. We don't need that today. But the point is, there is just one accept configuration that's relevant. And once again, we're going to consider the configuration graph of how this Turing machine can behave when we run it on an input word W. So again, and this configuration graph is definitely a directed graph. It says from one configuration of the Turing machine can make one step to another configuration by moving its head, writing something on the tapes, and changing the Turing machine state. And when a Turing machine can make a step in one direction, that step is not in general reversible. So it's very important that we're looking at paths with directed graphs here. So any input word W determines the configuration graph. G, let's call it G M sub W, G sub M W, so of M on input W. So let me remind you again what configurations look like. This is the third time we've done this, but just to, there's an important, each time there's a different important point to make about the configuration. The configurations in G and W look like, well, we have a state. So in any configuration of the Turing machine is in some state, little q. It will have its input tape. We're just talking about a Turing machine that accepts and rejects words, so it doesn't have an output tape, but it has working tapes and an input tape. So the input tape, we have always the input W, the input word W on the input tape, because the input tape, here it's important, only has a read head. It doesn't have a write head, so this word never changes. So W on input tape plus there's the tape head position on the input tape. So input tape plus the input tape head position. And then we have whatever is on the output tapes, B1, BK, sorry, on the working tapes, on the K working tapes, plus, again, K head positions. But the important thing that was never really important to us before, but is very important now, is that this input word W never changes. So actually, to record all the information we need to talk about what to distinguish one configuration from another, we don't need to look at this information. It will always be there on the input tape. But to record what can change in the configuration, we only need to record everything else. So this never changes. So how much information do we need? Well, to record a configuration, here we have, this is constant number of bits, the state, there are a fixed number of states. The tape head position, well, this can be recorded by a binary string that represents the index of the tape head position, counting from 1, say, for the leftmost symbol of the input position. So this is, so to record every possible head position on the input tape, you only need log of the length of the input number of bits. So this is, so because we're ignoring the input tape, we can get away with O log of the logarithm in the size of the input word here. And here we've got, well, what we know is that the total amount of space that we're using is bounded by C times logarithm of n. So all this information together, the lengths of all these strings together is bounded by C logarithm of n plus K head positions. So each of those is going to again take logarithm of the length of W. Each of these K, which length of W is n, each of these K head positions is also going to require logarithm of W information. But we've got some constant amount of times logarithm of W plus another constant amount K times logarithm of W. Any constant multiple of a logarithm, that's a big O of the logarithm. So this is also big O of log W. Okay, so for some constant K, configurations can be encoded C, capital C, say for configuration, can be encoded as strings. Code of C, string of binary bits of some K times A times log of the length of W. And the point is that now we're going to give a deterministic logarithmic space reduction . Oh, okay. We're going to give a deterministic now log space reduction that constructs from the above information, so from the configuration graph, from M and W, constructs G as T, which is the G is the adjacency matrix of the configuration graph, adjacency matrix of the configuration graph. S encodes the top 0, 1 to the k times log w is such that S is encodes the starter configuration and T encodes the accept configuration. And then we see, well, if we then give this as an input to path, path will accept it if and only if there's a path in the configuration graph from start to accept, which means that our machine M accepts the word W, the if and only if. So this is, so G, so then GST is in path, if and only if there is an existing path in configuration graph for M on W from start to accept, which is if and only if, because M was assumed to be a Turing machine for the language L, so if and only if W belongs to L. So sorry, I just said a deterministic, we're going to give one, I haven't actually given the reduction yet. So that's, I should clarify that, we shall give so how do we do that? Well, what we want is, given the Turing machine and its configuration graph, we want to, given a Turing machine, we want to have this reduction that, given the input W, will produce GST. Okay, so the reduction works as follows. The deterministic log space reduction works as follows. So we know the Turing machine M. We're allowed to use this to design our Turing machine that's affecting the non-deterministic log space reduction. The Turing machine that's affecting the reduction will take the input word W and needs to work with that information. And what it does is it does the following loop. It executes a nested for loop. So we execute a nested for loop. So for I in 0, 1 to the k times. So we've got the word W as input, so we can work out k times some appropriate ceiling of log W. That's done. And then we're going to cycle through every possible representation of a configuration in the configuration graph. We do that for I, and for J, it's also representing. We're going to go through every 2 configurations. And the point is, what we're going to do, we want to build, I'm doing this so that we can build the adjacency graph of the configuration graph. And so we're basically cycling through rows and columns, indexing them here. And for each row and column, we're then going to add a 1 if there's an edge in the configuration graph, and add a 0 otherwise. So insert 1 in the adjacency graph, adjacency matrix, if I equals C and J equals C prime for configurations C prime with such that C makes a single step. And all this, if you use a sensible encoding of your of your configurations, so you can nicely read off what the head positions are, what the current symbol being looked at, and so on. All this checking can be actually quite easily done in logarithmic space. So otherwise, for else, insert 0. Insert 0. And then we're basically done. Except what we need to check is that it takes the right amount of space. Well, there's a bit of working to be done here to check whether or not there's an edge here. I've just told you that can be done in a small amount of space. You just have to believe it. If you go think back to the Cook-Levin proof, everything's very local. So you just need to see whether there's a step in a Turing machine. You just need to align the heads in the right position. You've got some finite amount of space. You get some finite amount of space that codes up the transitions of the Turing machine, and you just check that, if this string says we're in this state with this head in this position, then in our transition table for the Turing machine, indeed, we do the appropriate operations that take us to the next step. The important thing is the amount of space that I and j take up. So these two are part of the algorithm. We can put them on different tapes, but this is certainly part of the working tape. We need to remember the configurations we're iterating through. But each of these takes space k times log of w. So but the algorithm is clearly deterministic. It takes, we didn't make any non-deterministic choices. The algorithm takes space big O of k times log of w. But the length of w, well, that's n. That's our input that we're measuring, the size of the input we're measuring. So this is indeed big O. So this is log n to the k. So that's big O. Well, anyway, it's k log n. So it's certainly big O log n because it's a constant multiple log n. So we're done. Right, so actually, once again, I'm not going to have time to go back to last week's incomplete proof, so that can get postponed until next week. It's a pity, it's a really beautiful little thing, but it will basically take about 13 minutes or something like that to present. I think it's better now that we have a pause, and then we're going to go to our 2 presentations. One of the speakers not here. I mean, sorry?
You should call me in like 5 minutes.
Oh, okay, that's fine, because I would like you two to go, you're going to speak in English. Yeah. So the first presentation is going to be in English, so I'll put that one first, just in case anybody, I don't know if there's anyone that doesn't speak Slovene here, but in case there is, then you can leave at the end of the first presentation. Okay, so let me stop the recording.